Okay, welcome back to Calc 2's section 6.7 now, physical applications. Um, those of you that are currently taking an analytical physics class may be coming across some of these problems as we're hitting them now in calculus. I am just going to kind of briefly go through 4 different types of problems where integrals are going to be used to help solve them. Now, in your physics class, you may be working on problems where you have things like a constant density and a constant force and where it's not variable. Where integration comes in is when we start talking about things like variable density, variable force. In those cases, when things are variable and they're not consistent through the whole application, or the whole physical object, then we have to use integration. So that's what we're going to look at now. So we're going to start with a very, very simplified mass type problem. So we all remember what mass is. Mass basically is one of my colleagues calls it the quantification of existence, of any physical existence. So any physical object has mass, and mass is, you've learned in your high school physics classes, density times volume. So how dense an object is and the size of the object will impact its mass. So if you think real quick, like a wiffle ball versus I'm going to say a bocce ball, so not everybody knows what a bocce ball is, but it's a very dense round ball that you roll on the ground. They might have the same volume, but clearly they have different densities. One is a much lighter density, the other heavier density. So their mass are going to be completely different. So, think about that. But again, we're going to be talking about something with variable density. If it was a constant density, hey, we'd be done. We would just use, hey, mass equals density times volume. We can move on. But if that density varies across an object, you can't just do density times volume. That's where the integration comes into play. But we are restricted right now with one-dimensional objects because we have not yet moved on to multivariable calculus, which you will do in Calc 3. So our objects are going to be, for this particular, like I said, this is a simplified mass problem. They're going to be very simple. Think of a one-dimensional rod, right? Very thin one-dimensional, rod here. And almost think of it as a line segment. But this rod would have, maybe it's denser here and less dense over here, okay? Has a variable density throughout it. So again, you can imagine taking cross sections and, working through summing up these cross sections into infinity, and hence the second you do that, we have an integration. So in this case, mass would be the length of your rod from A to B. And that length is going to essentially give you your volume because we're just doing one-dimensional. So that's where your volume's coming in that length. And that's covered because you're taking it from A to B. And we're going to use rho of x, and that's what this symbol is, the Greek symbol for rho, and that's going to represent our variable density function. So throughout this whole unit, your density function is rho of x. So your mass, simply becomes that. And I said we're very simplified. This first type of problem we're going to look at, and we're going to do a total of 4 types of problems. 4 problems. So this first one is one of the more easier problems. You just need to remember, just take from A to B the length of your object times the variable density across that object and take the integral of that. So for example, let's take a look at number 14 in our textbook. As always, I will just pick some odd problems from the text to go over. And this is called mass of one dimensional objects. And the mass of a one-dimensional object is the integral from a to b, rho x dx, where this is just represents a thin bar or wire. Just think of a wire. Think of it that way. On some interval of x between a and b, with a variable density function of rho. All right, so in number 14, let me pop it in my book I have in front of me here. We want to find the mass of a thin bar, one-dimensional thin bar, given that rho of x equals 1 plus sine x, and that x is between 0 and pi. So as you can see, this is not a difficult problem. We're simply going to take the integral from 0 to pi of 1 plus sine x dx. And we can do that rather quickly. 1 goes to x, that becomes minus cosine x from 0 to pi. So plug in pi, I get pi minus. What is the cosine of pi? If you think of your cosine curve, cosine of pi is -1 minus 0 minus, and what is cosine of 0? Cosine of 0 is 1. So, yeah, we get pi plus 1 plus 1. And we're done. So, the first set of problems are, I would say, pretty quick, just mass of one-dimensional objects. Well, we're going to get a little more complicated now. That was the first one. Like I said, we're going to do 4 of them. And this next one, we're going to move away from mass, and we're going to talk about work. So again, the basic equation in physics for work is a force on an object, you know, whatever the force is that's acting on that object, times the distance you move the object. So work represents, you know, how much energy does it take? What is the change in energy when a force causes an object to move a certain distance? So again, as you will when you first learn this in physics, if it were constant, we're done. We just use this formula and we don't need to worry about it anymore. But what we're going to talk about and what we're going to use is a variable force. So in other words, the force is not going to remain constant as the object moves. And the example we're going to use is something with springs. So think of a spring for a minute. So I want to set this up. And let's just talk about springs, okay, in order to use that, because you'll see right away why there's a variable force with a spring. So let's suppose we have, my spring is not going to look very good, and I apologize for that, but I will do my best. So we have a spring, a coil, right? And that coil's just sitting there at rest. And that's what it looks like at rest. That is a really bad coil, and I apologize for that. So we're going to put it in blue. When a coil is sitting at rest, we say it is in a state, it's in equilibrium. Okay, nobody's touching it. That blue fake wall I have there isn't really a wall. Nobody's touching this coil. It's just sitting there And we're going to say that the X value when it's at rest like this is just 0. All right, sitting at rest. Now, we can do one of two things to this spring. You've probably worked with springs before. As we speak, my car is in the shop because the springs popped. As you can imagine, I had no suspension. And what was supposed to be a 4-hour job is now on about the 12th hour because they're having a heck of a time at reattaching the springs. So now, one of the things you can do with a spring is stretch it. Right? So, look at that. Let's do it underneath, actually. So I'm going to stretch my really poorly. See, I stretched it out. And now it's stretched. So this was equilibrium, right? It's pulled out. And when it is stretched, we are actually applying a positive force. Okay? And that positive force occurs when an X itself, the position, is greater than 0 now. And the force is positive. And then, of course, in the same way, we can squish our spring. That's a really bad spring. Right? So this is where equilibrium would be, but we've compressed it. And when we compress it, our X value is now less than 0, which means we are exerting a negative force. Now, here's the thing. The force it takes to just move the spring from here to here is going to be less than if I wanted to move it way out here, right? That's why our force is variable. Same for compressing. If I try to compress it even further, that force it's going to take to the energy it's going to use to make that distance is going to be greater. And that's why our force is variable. And that's why we can't just say, hey, work equals force times distance. That's not going to work. In fact, when we're dealing with springs like this, we have something called Hooke's law. And according to Hooke's law, the force required to keep the spring in a compressed or stretched state, so the force required to keep it in this compressed or stretched state, X units from equilibrium, that force is equal to some constant times X. And this constant, regardless of the direction you're actually moving the spring, the constant is a positive value. And in a way, it measures, and it has to do with the stiffness of the spring. When I was young, we had these things called slinkies. They were not very stiff. You could compress and stretch that thing pretty easily. But I can imagine what's causing my car today to take so much time is they are very, very, very stiff strings. So the K on a slinky versus the K on the springs that are keeping the suspension together on my car are very, very different. But again, it's always a positive value, whether stretched or compressed. What changes is the X. Of course, if you're stretched, you have a positive X, and hence you're going to have a positive force. And if you're compressed, you're going to have a negative X, and hence a negative force. All right. So that's kind of an overview of Hooke's Law. Let's do one of the problems in our textbook and kind of use this information to take us through one problem. We are going to do number 24. This is in 6.7. And I'll pull this down if needed at any point. So in number 24, we want to suppose a force. Do you all know the measurement for force? We are going to use newtons as our measurement for force. Suppose a force of 30 newtons. 15, sorry, I was reading the wrong problem. Suppose a force of 15 newtons is required to stretch and hold the spring exactly 0.25 from its equilibrium meters. And that makes sense. We're stretching. It's a positive distance from equilibrium. We're good. So we're going to go through a couple things. We can use the information given to find our constant. So we're going to assume our spring obeys Hooke's law. And if it didn't, well, we wouldn't be here. We wouldn't be doing this problem. We want to use the information given to find our constant K. All right, well, that's pretty easy. If you recall up here, we said that the force equals F of x equals K times x. So x is 0.25 equals K times 0.25. And that force we said was 15 newtons. All right, so using that information up there, K itself should equal 15 newtons divided by 0.25 meters. And that is going to give us 60 newtons per meter. And we have K. But once you have that constant, because it doesn't matter at any point, that K, that stiffness of the spring, isn't going to change. The force required is going to change, but the stiffness itself, that K, will remain the same. So let's take a look at a second piece to this. So here it is. Now, next question. How much work so we're going to switch to work. How much work is required to compress the spring 0.2 meters from equilibrium? So if you recall, the integral for work, oh, we didn't even do the integral for work. We just did work equal, I didn't do the variable for work. All right, so we did state that work, of course, is force times distance, but that force is going to be variable. So we have to sum that force over infinitely many small distances. When you sum something over infinitely many small distances, we have an integral, right? It's the limit as n goes infinity and the summation up to n times. So work is then going to be equal to the integral from A to B, the distance it actually travels, of f of x dx. Nice, simple integration. All right. So force times distance is going to be our force across the variable, all these distances. So now, let's think about what's happening. We want the work required to compress. So remember, equilibrium is x equals 0. We want to compress the spring to x equals 2 meters from equilibrium. Because it's being compressed and moving to the left, that's a negative 0.2. But our starting distance is 0, and this is important. When you're setting up your integral, your initial location is 0. You're going from 0 to negative 0.2. There you go, negative 0.2. You're so used to going in a certain direction, you want to make sure that your equilibrium, your initial, is always the lower end, the lower limit of your integral. And we just found our K is 60. We said that Hooke's law, the force is equal to Kx. So our force equation is going to be, in this case, sorry about that, hit the wrong button, 60x dx. And that's it. So what's that give me? 30x squared when I differentiate from 0 to negative 0.2. Do the work, and you get 1.2. Now, let's talk units for work. So we have a distance times a newton. What is a unit when you take a distance traveled times a unit? We have something called a joule. So we call them joules is our unit for work. Joules as in Joules. And it's that simple. So now for the next question, let's take a look. How much additional work is required to stretch the spring from to stretch the spring 0.3 meters if already at 0.25 meters. So remember, when we started, we knew that we could stretch and hold our spring at 0.25 meters. So the question is, how much additional force now is needed, additional work is needed to go from that 0.25 to 0.30? And this is just a matter of distance again. That force is still exactly the same, 60x. So where are we initially? This is where you got to be careful, because that initial position needs to be your lower limit. Initially, we are at 0.25. We are going to stretch it an additional 0.3 meters. So where are we going to end up if we are at 0.25, so remember, you got equilibrium, we are at 0.25, we want to add 0.30, we're going to go to 0.55. So just make sure you put the right numbers in the right location. And this just is a matter of reading the problem carefully and making sure you write down what's expected from 6dx dx. So again, not a difficult problem integration-wise. And if you do all the math, I'll leave you to do all the math on your own. You get 7.2 joules. So now, those were the kind of lighter problems of the chapter. We're going to move on to two that are a little bit more complicated. For this third one I'm going to do what's considered a lifting problem. So when we talk about a lifting problem, I want you to imagine like a building and maybe a chain off the building. All right? And we want to lift, basically, when we're looking at, when you use the chain to lift an object up. Well, what we're doing here is talking about vertical force. And if you're discussing vertical force, there should be something really important that comes to mind. It's that thing that kind of keeps our feet on the ground, and that's gravity. We must consider gravity. When we're talking about vertical force. So, when talking about vertical force and gravity, force is actually equal to the mass times gravity. For gravity, for these problems, we're going to use our metric system to just do 9.8 meters per second squared. And mass, we're going to use this anytime, and we're going to keep, this is useful, and this is what it is whenever mass is measured in kilograms. So I want you to keep that in mind. Mass, we want to make sure we keep it in kilograms. So it's not in kilograms. We need to put it into kilograms. And we're going to use gravity of 9.8 meters per second. Because gravity changes with this addition, or I'm sorry, force formula changes a bit with this addition of gravity, our work function changes a little bit, because remember, work was force, right? I'm just going to use force times distance, but force is mg, and now you have distance. All right, so we just adjust our formula a little bit, which is going to greatly adjust it when we move it into our integral. Because again, just like with our spring, it's going to be a variable force. The force it takes when the object is here is going to be different from the force it's going to take when the object is there, and when it's there, and when it's at various parts. And that's due to the gravity that's being pulled on your object. So it is going to make a difference, which means we have to do all these little summations. Essentially, and bear with me on this one for a minute. Again, this is for constant force. For variable force, which is what we're working with, we need to use an integral. All right? So our integral is going to go from 0 to L. And we're going to let L represent the top distance, right? From 0 to L. So we have our mass, which is our, right, we got our density here, times gravity. Now, the distance. You're going to start at L, and it's going to be whatever is L minus the exact point it is along. So think of this as a y-axis, right? Because we are looking at a vertical distance, we are going to differentiate now with respect and change over the y-axis, dy. A little bit more complicated formula. And maybe it'll make a little more sense if we go through a problem. So, think of this as, your mass, of course, just to try to remember your formula, that's going to be this times dy, right? That's your mass. Gravity, and this is just your distance. So it's all here. In the formula, we're just kind of adjusting it for that variable, that change. All right, so here's the problem I want to do in this case. And it is number, 1 second. Is it the rope? Yeah. 60-meter rope. So for this case, we are going to do number 32. 32. Coiling a rope. So we have a 60-meter long rope. So there you go. So there's your L. Right away you see that L is 60. Right? You get the 60-meter long rope. 9.4 millimeters in diameter. Hangs freely from the edge of a building. The density of the rope is 55 grams. How much rope is needed to pull the entire rope to the... How much work is needed to pull the rope? Well, let's just go into our formula and see what we have here. All right, we know we got 0 to 60. That part was easy. So we need this density. Right now, it is in grams. If you recall, we need to convert it to kilograms. It needs to be in kilograms because the gravity, the 9.8 meters per second, is for when a mass is in kilograms. So we got to convert 55 grams to kilograms, and that's pretty easy to do. You would just divide by 1,000 kilograms. So we're going to change that to 55 over 1,000. We have our gravity, right? We know that is 9.8. We can use that now because we converted grams into kilograms. And we're going from 60 minus y dy. That's actually it. Once you get it down and you make sure you have all the pieces, that's all you need to do. So it's 55 over sometimes 9.8 times 60y minus y squared over 2 from 0 to 60, and you can do all the math. And if you do all the math, you should get 970.2. I didn't worry about the measurements as we went through because I know the work is always going to be in joules. All right. One more problem, or type of problem, and this one has to do with pumping water. Pumping water. So here's the idea on this one. We want to, we'll just work with a cylinder. Suppose we have water in this cylinder. All right. The cylinder could be full, so at some point it's at various levels throughout. And we want to pump it into something else, right? Into some sort of output. So this one's kind of interesting. The idea behind it is you're taking these cross sections, right? All cross sections. And you're moving each cross section into the new container. Now there's a lot of different parts we need to do that, but the formula is still going to look very similar. And we're going to try to calculate the work that it requires to make this move. So the work formula itself is pretty much the same. We'll talk about each of these pieces in a minute. But we need to add something. All right? And the part we need to add is the area of each of these cross sections. And that's what our A sub y is. We're still doing vertical movement and vertical work, so we're still going to differentiate with respect to y. We still have a distance. We'll call this the height minus y dy. But let's go through each of these little pieces for a second. First, density of water. We're going to use a standard 1,000 kilograms. Per meter cubed, and we're going to keep that as a standard. Obviously, we're going to keep our 9.8 per meter squared. This is going to represent the area of the cross section, and then of course this is the distance the water travels. So h is the height where the water is going to end up. So in other words, wherever the output is, this is your h distance. That's going to be your h. So it's going to be h minus whatever these y values are. All right. Similar, but a little different because we had to add in that cross section. For this one, let's take a look at think it's number 36. We're going to empty a tank. So we have a cylindrical tank of water, has height 8. And radius 2 meters. So, let's suppose the tank is full. How much work is required to pump the water to the level of the top of the tank and out of the tank? So I guess you can imagine this tank, right, is submerged in the ground, and you are pumping the water that is the exact height of the tank. Does that make that? That's what you're doing here. So how much work is required to pump the water out of the tank to a level that is the exact height of the tank? All right. So I know, all right, it's 8. We have a radius of 2. So work equals. Now, let's talk about A to B. That's going to represent your water levels. You're going from 0 to 8 because we said the height of the tank was 8. Our water has a density of 1,000. Again, I'm going to do away with measurements because I know I'm going to get my answer in joules. 9.8. So now I need area. Well, area of a cross section, right, is just going to be pi r squared. So 2 squared times pi, so that's going to be 4 pi. And then we need the height, which was 8, minus the variable y, the various y's, because it's going to be different levels for each iteration. dy. That's it. The hardest part is probably remembering the different parts of the formula. On a test, I would likely say, hey, for this problem, rho equals, and use gravity 9.8. Because in case you forget that stuff, I don't want you to get the problem wrong because you forgot that on the test. So I would likely give you that. Right, so it's 1,000 times 9.8 times 4. What's nice about these problems, once you get them set up, the integration part is really kind of easy. Oh, and if you do all that math, you get something like 3, this is approximation, like 3.9 million, something like that. Depending on how much you estimated pi. So you get about 3.9 million, almost 4 million joules. So that's a lot of work. Okay, so that takes you through a few problems. You know, I suggest you kind of look over the textbook. They have additional problems in there. And that's it for this lesson.